moments.
Yeah.
By the end of this section, you should be able to calculate the moment of a force, apply the principle of moments, find the center of gravity of an object.
Yeah.
We will learn the definition of moment and then apply the principle of moments for some questions. All right, you can see here moment of a force. The force is shown and the distance from the pivot. This pivot point is also called the axis of rotation. Okay, we assume that the object is fixed at the pivot point or axis of rotation, but it can rotate about that point. Okay, and the distance we can take as the perpendicular distance from the axis of rotation or pivot point to the line of action of the force. Line of action is the direction or line. If you draw a line along this force, okay, if you draw a line to show the line on which this force is on, that is the line of action of the force. So if I draw a line passing through this, that is parallel to this, along this, that is the line of action of this force.
Yeah.
And this is the definition: moment of a force, okay, moment of a force is equal to the force times the perpendicular distance from the pivot to the line of action of the force. This word perpendicular distance has to be mentioned. The word perpendicular is very important. If you write moment equals force into distance, that's not correct. You won't get the marks. You have to say moment of a force is equal to the force into perpendicular distance from the pivot to the line of action of the force.
Okay.
Perpendicular distance from the pivot. So you see perpendicular distance, it makes a 90-degree angle with this force. That is why we say perpendicular distance. Over here the angle is 90 degrees. So perpendicular distance from the pivot to the line of action of the force. If you draw a line along this arrow, that is the line of action. Okay, so that line of action should make a 90-degree angle with the distance from the pivot to that line of action of the force. Okay, so this is the definition. Make sure when they ask you the definition, you write this, and this word perpendicular distance, word perpendicular, has to be there. In mark schemes, they look for that word.
Okay.
Okay. Then we have, okay, so here is another example. Now, if you hold something like this, maybe a book or a cardboard, you hold it at this end. When you hold it at this end, it doesn't move about this. It doesn't move here. It is fixed here, but it can rotate about this point. So this is the pivot or axis of rotation. Okay, this is the pivot point. You see here the word pivot point. We can also call it the axis of rotation. Then when you hold it here and just leave it, hold it here, then what can happen is this object, this book can rotate about your thumb or where you're holding it, which is the axis of rotation. The weight force is downwards, so this will cause the book to rotate anti-clockwise. You see, this force is trying to pull this down. It's trying to rotate this book about this point in the anti-clockwise direction. This force is trying to pull it down this way. So when it tries to pull this down this way, because it is fixed here, but it can rotate about this point, the book turns anti-clockwise. It moves in that direction. If you are still not familiar, you can take a book and try to keep it in this position and just don't hold it too hard, then it won't turn. Okay, slightly hold it, then you will notice that it turns this way. Okay.
Yes.
When finally what will happen is it will come to this position. At this position, it doesn't try to rotate. So even if you hold it as lightly as possible without falling, it will not rotate clockwise or anti-clockwise. Okay, because this weight force, which is vertically downwards always, the weight force is vertically downwards towards the center of the earth. The weight force is having this its line of action, so that the reaction force is also in that line of action. Now the reaction force or contact force is what keeps the book held by your fingers. Okay, there is a contact force. There is also a force of friction. Okay, so now in this case we can consider the force of friction. Okay, because if it's a contact force, it has to be perpendicular. So we can say the force of friction is vertically upwards, and the weight force is vertically downwards, and they are in the same line of action. Over here, the contact force, the frictional force is upwards, vertically upwards, because this is trying to move down, we can say, but this is vertically downward, but they are not in the same line. You can see this dashed line is the line of action. Okay, the line of action of the frictional force would be this one, but the line of action of the weight force is over here. If you draw a line passing through this red arrow parallel along the red arrow like that. Okay, so if you draw a line something like that, that is the line of action. This is the line of action of the weight force. Now that is the line of action of the weight force. Over here we have the line of action of the frictional force. They are in two different lines. They have two different. They are in two different lines of actions. This is the dashed line showing the line of action of the frictional force, we can say. Then what happens is this moves down so that the line of action of the frictional force, which is actually shown by this red line, is in the same line of action as the weight force. So when it is like this, we can say there is no net moment. Okay, no net moment, so it doesn't rotate. So when the frictional force and the weight force are in the same line of action, there is no net moment or resultant moment, so it doesn't rotate. But over here it rotates because they are in two different lines of actions. Okay, so this is where we learn about the principle of moments. The principle of moments states that if the sum of clockwise moments is equal to the sum of anti-clockwise moments about any point, then the object will be in equilibrium. Okay, so if you consider this one, let's take this plank for example. Okay, the weight of all of these will act downwards. Okay, so downwards, then there is a contact force here. The contact force exerted by this on this plank is down. Okay, then the contact force exerted by all of this is on the plank is downwards. Okay, and it is equal in magnitude to the weight of them. Equal in magnitude here to the weight, the contact force here, because it is if it is in equilibrium. Okay, so balanced moments create an equilibrium situation. There are two conditions for equilibrium. The first is the resultant moment should be zero. Okay, the resultant moment should be zero, and the second is the resultant force should be zero. I can write it down here. Okay, so for an object to be in equilibrium, there are two conditions. The first is these are very important in the exam papers. They have asked it. Okay, so for equilibrium, the first condition is the resultant moment sigma m. This indicates resultant. Resultant moment should be zero. Okay. Resultant moment should be zero. Okay. And the second condition is the resultant force should be zero. What we mean by these two is, the first one, resultant moment equals zero, means the sum of clockwise moments should equal to the sum of anti-clockwise moments. So what this means is the sum of clockwise moments about a certain point should equal the sum of anti-clockwise moments about the same point. Now we will learn what the clockwise moments, anti-clockwise moments are. And what this means is the total forces, sum of forces in one direction should be equal to sum of forces in the opposite direction. So if the sum of forces in one direction is equal to the sum of forces in the opposite direction, the resultant force is zero. Okay, so that's what this means. So when these two conditions are met, the object will be in equilibrium. The object will be in equilibrium. Okay, so let's go back to the lesson we were doing. All right, so if you take moments about this point where this plank is in contact with this object, there is a contact force exerted by this red ball downwards on this plank, and then by this white ball downwards on the plank, again the same plank here. So what will happen is, if this is in equilibrium, then it won't move, it's stationary. All right, so the clockwise moments should equal the anti-clockwise moments, and the total forces upwards or in one direction upwards should be equal to the total forces in the downward direction, so on the plank. So over here the forces are, I can draw a free body force diagram to indicate this. A free body force diagram for an object is a diagram which is showing only the forces acting on that particular body. Okay. So if I draw the free body force diagram for the plank, I have to draw the force, only the forces acting on this plank. Okay, so let's say this is the plank, right? So we can have a look at this diagram. Okay, so let's say this is this plank I'm drawing here. Okay, then there are three forces, or rather four forces acting on this. So this is the free body diagram. In short, we say FBD, FB, or FBD, free body force diagram. FB, also we say in short FBD, free body force diagram or free body diagram. Okay, so this is the normal contact force exerted by the red ball on the plank. You can call that R1, for example, or RB because it's a red ball, or reaction force exerted by the red ball on the plank. Then over here we have another force, which is the reaction force exerted by the white ball on the plank. The reaction force is also called the normal contact force. There are several names for the reaction force. One is the reaction force, another name is contact force, another name is normal contact force, normal reaction force. Those are the four names. Okay, why we use the word normal is because normal means 90 degrees. So the reaction force or contact force acts at 90 degrees always. From the surface it is exerted from. So this force is exerted from the surface of the red ball. So it has to be perpendicular to the surface of the red ball. Okay, and you know this here it is horizontal. So when it is perpendicular to the surface, it has to be perpendicular to the surface of the plank. So over here also it is 90 degrees. Then there is another reaction force by this white ball, which is upwards on the plank. Okay, so there is a reaction force exerted by, again, the big white ball. I'll call that RW1 on the plank, which is upwards. Okay, now there is another force which is the weight of the plank. If this is a uniform plank, the weight of the plank will be at the center. Okay, the center of mass will be at the center. Because it's a uniform body, mass is distributed evenly. So the weight force will act from the center of mass, which is at the center. But for this calculation, we'll assume the mass of the plank is negligible. Okay, in some questions they ask you to assume the mass is negligible. Okay? So for simplicity, we can assume the weight is negligible. But if there was a weight, it will act in the middle. If this is a uniform plank, which is at the center, means center of mass. Okay, the center of mass or center of gravity of a body is where the weight of the body acts. Is assumed to be active if we consider to act. All right, then we have this. Now if you take moments about this point, okay,
Yeah.
if you take moments about this point, what will happen is the reaction force from the red ball. Now when you're taking moments about a certain point, you assume the object is fixed at that point, but it can rotate about that point. So if you're taking moments about this point here, what you do is you assume this plank is fixed at this point, but it can rotate about this point. So you can imagine there's a hole made here in the plank and there's a nail through that. Okay, so then it can rotate like a seesaw. So you assume it is fixed here by a nut or something. There's a hole here, so it allows it to rotate, but it doesn't allow it to move. You can't translate it. You can move it from one place to another place. Only thing is it can rotate about this point. So that is what you have to think when you are going to take moments about a certain point. Okay? So if you are taking moments about this point here, where this reaction force of the big white ball is acting, we assume it is fixed at this point, but it can rotate about this point. Okay, so what will happen is if it is fixed at this point and it can rotate about this point, this reaction force, which is acting this way downwards, will try to turn this plank in the clockwise direction. Okay, so if you assume this is the only force that is active and this is fixed at this point, so like a seesaw, let's say you sit on this side of the seesaw, then what will happen? The seesaw will turn in the clockwise direction. Okay, about this point. So this force, which is acting vertically downwards on the plank on the right side, will try to turn the plank clockwise. So what we say is it produces a clockwise moment about this point. So you have to also say about which point it is trying to turn this clockwise or anti-clockwise. Okay, so this reaction force at B from B is producing rather a clockwise moment about the point, this point. Okay. Whereas if you consider this reaction force, the reaction force exerted by the small white ball on the plank is trying to rotate the plank about this point in the anti-clockwise direction. So again, you can imagine this seesaw, somebody sitting here, then when somebody sits here, the plank will turn this way, okay, which is in the anti-clockwise direction. Okay, so this force will try to turn this in the anti-clockwise direction, which is in this direction. This force will try to produce an anti-clockwise moment about this point. This force will produce a clockwise moment about this point. So if it is in equilibrium, then the sum of clockwise moments should be equal to the sum of anti-clockwise moments, and also the sum of forces in any direction should be 0. That means the resultant force should be 0. Now we can actually find first the moment and then the reaction for the resultant force by writing equations. So they will give you these quantities, maybe R, W, RB, and something, 1 or 2 unknowns are there which you have to find. So let's consider over here, for example, let's say this is the distance from the axis of rotation, which we assume to be here. Let's call this x1, and then this distance we can call it x2. It has to be a horizontal distance. Draw this. Okay, so we can call this x2. Then we can write an equation, but we have to, like I said, we have to say where we are taking moment, about what points we are taking moments of. Okay, so if in equilibrium, if this plank is stationary, okay, if it's stationary, that means it is in equilibrium because of Newton's first law. Newton's first law, if states, we can say states that if a body is in equilibrium, that the sum of if a body is in equilibrium, it has to be either stationary or traveling with constant velocity. Okay, so if a body is stationary, so let's say this plank is stationary. Okay, if this plank is stationary, then we know it is in equilibrium. Okay, by Newton's first law. N1 means Newton's first law. Some mark schemes use this N1 to indicate Newton's first law. Okay, so N1 means Newton's first law. So if an object is stationary, then it is in equilibrium. Now we can say if this is stationary, then it is in equilibrium, which means the principle of moments apply. Okay, this is the principle of moments. The principle of moments is this. Okay, which is what? The sum of clockwise moments is equal to sum of anti-clockwise moments, or the resultant moment is 0. So 3 ways of saying the same thing. Principle of moments apply, or we can say resultant moment is 0. Also we can say the sum of clockwise moments is equal to the sum of anti-clockwise moments. But the principle of moments means is this: the resultant moment is 0, or the sum of clockwise moments is equal to the sum of anti-clockwise moments about any point. Okay. So we'll take moments about this point. Why we are taking moments about this point is because we usually take it at a point where the force is acting, so that the force gets omitted from the calculation. Now if you take moments about this point, what will happen is this force, the perpendicular distance of this force from the pivot is 0. Yeah. So when you apply that moment equation, moment is force into perpendicular distance. The perpendicular distance is 0, so this gets omitted from the calculation. Okay, so we'll write the equation now. If stationary, then it is in equilibrium. Therefore, the resultant moment sigma m is equal to 0. Okay, so you take moments about this point, then the clockwise moments is r b times x2 about this point. So resultant moment is 0. So that means the principle of moments apply. Now we also have to say about which point. Okay, we can say at the point where r at point. We can even label this with a letter. Okay, so I will use a letter at point O, let's say, or at point A. Okay, so point A is this point. At point A, okay, point A. Okay, so RB times x2 is equal to RW times x1. The clockwise moment is equal to the anti-clockwise moment. Okay, so this is one equation we get. Now the second equation we can get is the resultant force is 0, because if it is in equilibrium, then two conditions: the resultant moment is 0 and the resultant force has to be 0. So that means the sum of forces in one direction should be equal to sum of forces in the opposite direction, which means RW. Okay, so if we take in the vertical direction, let's say we take in the vertical direction, because there are no other forces in any other direction, only thing the forces are all in the vertical direction. So RW plus RB, the total downward forces, these are the only two downward forces acting on the plank. RW plus RB should be equal to RW1. These are the two equations we can get. Now all the calculations we will see are based on this. The sum of clockwise moments equals sum of anti-clockwise moments, and the sum of forces in one direction is equal to sum of forces in the opposite direction. This is what you will have in all the principle of moments calculations. Okay, now let's continue with this.
So if there are something called coupling movements or something.
What?
Coupling movements.
Yeah, we will see those. Okay, so that's also related to this. Okay, we have something about torque, if you consider a steering wheel. Okay, so we will see that. Okay. Now here is another example. Okay, so we don't know they have not told us what the force is that is acting at this point. So to make our calculation easy, we can take the moment about this point. We can also take moments about any point. Okay, we can take moments about this point. We can take moments about this point. We can take moments about any point. If it is in equilibrium, the sum of clockwise moments is equal to the sum of anti-clockwise moments. That is what we call the principle of moments. Okay, in the exam papers they ask you to state the principle of moment, state what is equilibrium. So again, you can see the principle of moments tells us that if the total of all the moments trying to turn an object clockwise is equal to the total of all moments trying to turn an object anti-clockwise, then it will be in rotational equilibrium. Okay, so here we have this produces rotational equilibrium. This can cause it to move up or down in a different direction, or also it can cause it to rotate. So that's why they use the word rotational equilibrium here, because the moments try to turn the object or rotate the object. Okay, then okay, so if you consider this example here, okay, so actually they are doing that calculation here. So you can see this diagram. I think the best thing is to take moments about this point, because they have not given the force, and also the distances from this point are all labeled. Okay, so best thing would be to take moments about this fulcrum. Okay, we assume it's going to rotate about this point, the tip of this fulcrum, and then pivot and then do the calculation. So we'll see in figure D. There is figure D. We can work out the weight of the beam if we know all the other weights and distances. Okay, weight of the beam is W0. This is the weight of the car. This is the weight of the dinosaur, W1. W2 is the weight of the car. W0 is the weight of the beam. Okay, Actually the weight is not acting on the beam. The weight of the dinosaur is not acting on the beam. The weight of the car is not acting on the beam. The weight of the car acts on the car. The weight of the dinosaur acts on the dinosaur. Okay, but we show it like this because the weight is equal in size to the reaction force. Okay, so if you consider the dinosaur, and if this is stationary, we consider the dinosaur, the weight magnitude of the weight on the dinosaur is equal to the magnitude of the reaction force exerted by the plank on the dinosaur. Okay, that is not a Newton's third law pair. A lot of students confuse this. If it's a Newton's third law pair, it should be the same type and acting on different objects. So over here, if you take the weight force of the dinosaur, it is acting on the dinosaur. Then the reaction force exerted by the plank on the dinosaur is also acting on the dinosaur, and they are different forces. So if they are Newton's third law pairs, they should be the same type and acting on different bodies. So the weight equals the reaction force is not a Newton's third law pair. All right. So why we take this like this is because now you know the reaction force and the weight on the dinosaur are equal in size because the dinosaur is stationary in equilibrium. So the sum of forces acting on the dinosaur are totally zero. Okay, but you know when the dinosaur is here, by Newton's third law, the normal contact force exerted by the plank on the dinosaur should be equal to the normal contact force exerted by the dinosaur on the plank. So over here you have the normal contact force exerted by the dinosaur on the plank downwards. That is a Newton's third law pair with the normal contact force exerted by the plank on the dinosaur. Now those two forces, the normal contact force exerted by the dinosaur on the plank here and the normal contact force exerted by the plank on the dinosaur, are the same type of forces. They act on different bodies. They have the same line of action, same size, act in opposite directions. And they also act for the same time. So therefore, that is a Newton's third law pair. Now, because that normal contact force exerted by the dinosaur is equal in magnitude to the weight of the dinosaur, we simply label the weight of the dinosaur like this. Okay, but remember, it is the weight of the dinosaur doesn't act on the plank. Weight of the dinosaur is the force acting on the dinosaur. This is the weight of the dinosaur, not so weight force acts on that particular body, not on any other body. Okay, but for simplicity we do it like this because the forces are equal in magnitude. Okay, so we can work out the weight of the beam. If now weight of beam acts on the beam, so that is fine. We can draw it on the beam. If we know all the other weights and distances, so if we know all the other weights and distances using the principle of moments, if this is in equilibrium, we can find the weight force of the beam. The beam is uniform, so its weight will act from its center. Okay, they say the beam is uniform. Uniform means its weight is the mass is spread evenly throughout the entire beam. So if you take the center of gravity, it will be in the middle because it's a uniform beam. The mass is evenly spread out everywhere throughout the beam. It's a uniform beam. So the center of gravity or center of mass will be in the middle. The center of gravity is the point where all the weight of the object is considered to act. The beam is uniform, so its weight will act from its center. The length of the beam is 100 centimeters. They have given this is 100 centimeters. Okay, so this is some toy. They are using 100 centimeters. So if x1 is equal to 20 centimeters, this one x1 20, the whole beam is 100. So then x2 should be 100 minus 20. So x2 should be 80. You can see here 80. Then x0, which is this one. Okay, so from here to here it is 50. X1 plus x0 is 50 because the center of mass or weight of the plank acts from the middle of the plank. So from here to here it is 50. So if we know x1, then 50 minus x1 will give you x0. So that is 30. So it's 50 minus 20, which will give you x0. That is 30. The dinosaur weighs 5.8 newtons. The weight of the dinosaur is 5.8 newtons, and the toy car weight is 0.95 newtons. Now we can use the principle of moments because this is in equilibrium. It is stationary by Newton's first law. You know, if it is stationary, then the resultant force should be zero. We can say it should be in equilibrium. So if it is in equilibrium, the two conditions have to be met. The resultant moment should be zero, the resultant force should be zero. So we can apply the principle of moments here, which states that the sum of clockwise moments about a point, any point, is equal to the sum of clockwise moments about the same point. Again, the sum of clockwise moments about any point is equal to the sum of anti-clockwise moments about the same point. This is the principle of moments. You should remember what the principle of moments is. It's very important. In some exam papers, they ask you to write it. Okay, so very simple. Sum of clockwise moments about any point is equal to the sum of anti-clockwise moments about the same point. Okay, so we have here. Now they are taking also. It's better if you say about which point you are taking moments. Okay, so here they have just written it, but they haven't said about which point the moments are taken. So you also have to say about which point the moments are taken. Now it has to be here, okay, because I know it when the equation can be written like this when the moment is taken about this point, but you have to say about which point the moments are taken. So let's call this point A. Then you have to say the moments are taken about the fulcrum or the pivot, this pivot that is at A, taking moments about A. So if you take the moments about this point over here, that is at the tip of the fulcrum, you have to think that it is the plank is fixed at this point and it can rotate about this point. Okay. Yeah. So this force, the weight force of the plank, will try to rotate the plank clockwise about this point. You see, this force is acting downwards. So again, think of it like a seesaw. If you're on this side and if you're sitting here, the force you exert is downward, so it will try to turn it and clockwise. So over here it will try to turn in the clockwise direction about this point. The weight force of the car, actually the reaction force of the car on this, will again try to turn it clockwise. This force will try to turn it anti-clockwise. Actually it should be the reaction force. The reaction force will try to turn this anti-clockwise about this point. So these two forces, W0 and W2, will exert a clockwise moment about this point here. This force will exert an anti-clockwise moment about this point here. And you know, according to the principle of moments, the sum of clockwise moments is equal to the sum of anti-clockwise moments. So we'll write that equation like what I mean. This is what they have given. So W1x1. So W1x1, the anti-clockwise moment. The total anti-clockwise moment is W1 times x1 about this point. That should equal the total clockwise moments. So sum of rather they should have written it the other way, because this W1 x1 is producing an anti-clockwise moment. Okay, so what they should have done is they should have written here sum of anti-clockwise moments is equal to sum of clockwise moments, because they have written the anti-clockwise moment here. Okay, which is exerted by the dinosaur on the plank. Then W0 x0, that is the clockwise moment exerted by the weight of the plank on the plank about this point. So you remember the formula for moment is force into perpendicular distance. So this is the force, the perpendicular distance, the 90-degree angle that the distance makes with the line of action of the force. So this is the line of action of the force. You can see the dotted line, dashed line. This is the line of action of the force. Okay, weight force, and this is the perpendicular distance from the pivot. It makes a 90-degree angle. So then the clockwise moment exerted by the plank on the plank about this point is W0 x0. So that's what they have here. Then the clockwise moment exerted by the car on the plank about this point is W2, the force, times the perpendicular distance from the line of action of the force. This is the line of action force to from the pivot to the line of action of the force, the perpendicular distance. See, perpendicular distance from the pivot to the line of action of the force. That is the moment equation. So this is the force This is the perpendicular distance from the line of action of the force to the pivot. So that is x2. So W to x2. Okay. So these two exert the total clockwise moment about this point. This will exert the total anti-clockwise moment about this same point. So that's how you get this equation. Now, since they have given us the values, we can directly substitute into the formula and solve for W0. You will get the weight of the beam as 1.3 newtons. Okay, and then learning tip. So they are asking you to, if you want the total clockwise or anti-clockwise moment, you take each one and add them. Like you can see, this is what we did. So there are two forces which produce a clockwise moment. So we take the sum of them, because it is the sum of clockwise moments which is equal to the sum of anti-clockwise moments, which is again the principle of moments. Okay, then center of gravity. Okay, again you should know the definition of center of gravity. In the exam papers they can ask you to write it down. Okay, so the definitions you should know are moment of a force. Okay, the definition of moment. Okay, then what principle of moments is, they can ask you to write this down. And the conditions for equilibrium, which like what I wrote here. Okay, the two conditions for equilibrium. And they can also ask you to define center of gravity. Okay, so here they have given that to you. Okay, the sum of all these tiny weight forces appear to act from a single point for an object, and this point is called the center of gravity. So that is center of gravity. Now in the other book also they had some definitions. Okay, so you can use this book as well. Okay, so you see moment of a force, the definition is highlighted in green here. Then about the principle of moments, that is also highlighted. Center of gravity definition was given in another chapter, I think in this book. Oh no, it's here, see. Center of gravity. The center of gravity of an object is defined as the point where all the weight of the object may be considered to act. Very simple. Okay, so you can use this definition. Okay, so again, the center of gravity of an object is defined as the point where all the weight of the object may be considered to act. So all the weight of the object is considered to act. That is the center of gravity. So we said the center of gravity is where the weight of the object acts. All right, so if the object is symmetric, it is easy to find where the center of gravity is. If the object is uniform and symmetric. Uniform means the mass is evenly distributed throughout it. Okay, so one part of the object is not heavier than another part. So the mass is evenly distributed. That is what we mean by uniform. So if it's a uniform body of a regular shape, then the center of mass or center of gravity will be in the middle. So let's say, for example, a flat circle. Okay, so you can imagine this is a circle made out of cardboard. We take a piece of cardboard and then cut out a circle. Then you will notice that when you keep your finger at the center and the circle horizontal, you can balance it. The reason you can balance it is because, okay, so if I draw something like this, okay, so let's say this is the circle, you are seeing the side view. Okay, let's say this is your finger here. Okay, so you can balance this. You can balance this like this because the weight force of that circle, flat circle made of cardboard, is acting like this downwards. Vertically downwards, the weight force acts like this. And your reaction force, which is the reaction force exerted by your finger on the circle, acts upwards. So both of these forces are acting on the circle. Okay, so now you can see both are in the same line of action. They are equal in size, opposite in direction. So there is no net moment. Okay, so no net moment about any point. If you take any point on this circle, the sum of clockwise moments is equal to the sum of anti-clockwise moments, and also the resultant force is 0. So therefore the circle will be in equilibrium. Okay, so this is the side view of the circle. So that's why circle is in equilibrium. But if you move your finger to this side, then what will happen? There will be a resultant moment. So it will rotate, it will fall, it will topple. Okay, then okay, so same thing applies for this and also applies. So anywhere, if you keep your finger anywhere, I mean at the center of gravity, and if the object is horizontal, then it will balance. Okay, if you take a piece of cardboard that is a rectangular in shape, or you can even try this with your ruler. If you keep your finger in the middle, because your ruler is uniform, it has a uniform mass, sorry, it's a uniform body, then you will be able to balance it. Okay, another way of finding where the center of gravity is by checking if it has any lines of symmetry. You would have learned about rotational symmetry in the maths class.
Yes.
So if you have any lines of symmetry, where the lines of symmetry intersect, okay, for a body in 2 dimensions, where the lines of symmetry intersect is where the center of gravity is. Always that center of gravity should be on the line of symmetry. And if you have 2 lines of symmetry, where the lines of symmetry, now I told you just now, the center of gravity should be on the lines of symmetry or line of symmetry. So if it is on the lines of symmetry, there is only one place for the center of gravity. So if there are 2 lines of symmetry, it has to be at the point where the 2 lines intersect, because it has to be on both or all the lines of symmetry. Okay, so if you take something like this, there are infinite lines of symmetry. The diameters of this circle are the lines of symmetry. So all the diameters pass through the center. So the center of gravity is in the center of this circle. Over here in a rectangle, there are 2 lines of symmetry. This one and this one. So where the 2 lines intersect is where you have the center of gravity, because the center of gravity has to be on all the lines of symmetry. But if it was a square, then the diagonals also will be lines of symmetry. If it was a square, okay, the diagonals will also be lines of symmetry. So you will see the center of mass for a square is in the middle. A line of symmetry is a line where if you fold it along the line of symmetry, the 2 sides will perfectly overlap. So if you take this rectangle, bend it at the line of symmetry, fold it at the line of symmetry, then the 2 sides overlap perfectly. If you fold this if you fold this rectangle along this line, then these 2 sides will overlap perfectly. That's why it's a line of symmetry. Same thing with the circle. If you fold the circle anywhere along its diameter, the 2 sides of the circle divided by the diameter will overlap perfectly. Okay, same thing here. You can see this is a line of symmetry. So if you fold this triangle along this line of symmetry, this side and this side will overlap perfectly. Okay, so here we have the center of gravity on this line, axis of symmetry. Yes. And also you can see there are equal amounts of mass each side of this line. So the mass of this side should be equal to the mass of this side, because this divides it by 2 symmetrically. Same thing applies for this. There are equal amounts of mass each side of this line. Okay, you can consider the term center of gravity and center of mass to mean the same thing. They are identical for objects that are small compared to the size of the Earth. Okay, I don't think you need to know the details of this. You know, if the object is in a uniform gravitational field, the center of gravity and the center of mass are at the same point. So that's what they mean by this. Now, if an object is very small compared to the size of the Earth, and if it is close to the surface of the Earth, now if you take the surface of the Earth, the field lines are vertical. But if you go look at the Earth from the moon, the field lines will be radial. Okay, so if it's a radial gravitational field, the center of gravity may not be at the center of mass. But what we will be discussing is objects in uniform gravitational fields. In uniform gravitational fields, the center of mass and the center of gravity are at the same point. Again, let's say if you take the surface of the earth, okay, so this is the earth, we take a small part of the earth, let's say where we are, for example. So if you take a small portion of the earth, the gravitational field lines are parallel to each other, like this. Okay, the gravitational field lines are parallel to each other, but actually they are not really parallel. Somewhere towards the center of the earth they will meet, so eventually this will be intersecting. If they are parallel, they should not intersect, but since this distance is very small and the earth is very large, those lines can be considered to be parallel. So this is a uniform gravitational field. Okay, uniform gravitational field. But if you consider, if you look at, so this is the surface of the earth, small part of the surface, but if you look at the earth from the moon, then the gravitational field lines are this way, like that. So it is like the radius of a circle. Okay, so all of them, you know, the center of the earth is there, let's say, so all of them are like that. So this is a radial gravitational field. Radial gravitational, you will learn this under gravitational field, radial gravitational field. Okay, so here we have a uniform gravitational field, okay, where the lines are parallel to each other. Here we have a radial gravitational field. But since we are talking about small parts of the earth, so objects very close to the earth, very small, so they are in a uniform gravitational field. And since they are in a uniform gravitational field, the center of gravity and the center of mass for the object will be at the same point. But if it's in a radial gravitational field, it would not be the same. But here we in this syllabus we can assume that they are at the same point. Center of gravity and center of mass are at the same point. They are the same thing. They are identical for objects that are small compared to the size of the earth. Okay, then if you have irregular objects, the center of gravity is not in the middle. For example, something like this, or even say Bunsen burner. You would have learned about stability and center of gravity. The lower the center of gravity, the more stable the object is, and larger the base area of the object, the more stable the object is. So yes, when we want something to be very stable, we have to have its center of gravity very low. For example, a Bunsen burner. The Bunsen burner will not topple easily because its center of gravity is very low. It's very low means it's close to the bottom of the object, and it has a large base area. So that makes the Bunsen burner very stable. The center of gravity of an irregular shaped object will still follow the rule, that is at the point at which the object, at the point which its weight appears to act on the object. A Bunsen burner, for example, has a heavy base, and so the center of gravity is low near that concentration of mass. The mass of the Bunsen burner is concentrated at the part that is close to the bottom of the Bunsen burner, the bottom part of the Bunsen burner. So that means the center of mass should be somewhere there. It's closer to the side where there is more mass. Okay, as there will be a great attraction by the Earth's gravity to this large mass. Okay. So now, okay, so if you consider something like this, now this is what I explained earlier. If you take this object, for example, the center of gravity is here, and then the reaction force is also at the same point, and they are having the same line, they are on the same line of action, like this. Okay, so let's say if this was the broom or this object, broom or whatever, okay, and then this is the pivot. Okay, so the support is here like this. Then the reaction force from the support is having the same line of action as the weight of the broom, line of action of the weight of the broom. Therefore, the broom will be in equilibrium because the resultant force is 0 and resultant moment is 0. So then it will be balanced. So another way of saying this is, if an object is balanced, the object is in equilibrium. Now we learned earlier, if an object is stationary, it is in equilibrium. when it is balanced also, it is stationary, so it will be in equilibrium. You will come across this also where they say it is balanced. So when they say balanced, you have to understand that the object is stationary or the object is in equilibrium, and therefore the principle of moments apply, which means the sum of clockwise moments is equal to the sum of anti-clockwise moments, or in other words, the resultant moment is 0, or moments about any point is 0. The resultant moment about any point is 0. Okay, now what happens is, if you shift this to this side, you can see the support is here, the center of gravity is now here. You move the broom to the left. Now what will happen is, this weight force of the broom acting on the broom, the weight of the broom which is acting on the broom, will try to rotate this broom about this support, about this point, in the anti-clockwise direction. Why? Because the weight force is pushing down here. It's pushing down like this, pushing down, pulling down. Okay. So what will happen is, if you take moments about this point, if you can even try this at home, you can take a broom and try to leave it like this, where the center of gravity is a bit on this side. Then what will happen is, it will try to rotate this way, which is in the anti-clockwise direction about this point. Okay, so to balance it, we can hang something like this. We use a mass hanger, slotted masses, hang it here until we come to a point where it balances. So if it is balanced, then you see the tension or the pulling force down from here, which is acting on the broom, is trying to turn the broom in the clockwise direction. It's trying to rotate it this way, about this point. The weight of the broom is trying to rotate it this way. So if it is balanced, then the sum of clockwise moments about this point, which is the moment exerted by this is the only force that is trying to turn it clockwise, should be equal to the sum of anti-clockwise moments about this same point. So here we have center of gravity, so it's trying to turn it this way. Okay, then it is in equilibrium, and we can use this method to find the weight of the broom, because we know this weight, we already know this, and we can measure the distances. So from here to here we can measure the distance, from here to here we can measure the distance, and since we know this mass, we can find the weight. So this weight times this distance will give you the clockwise moment about this point. Then the weight of this broom about the weight of this broom times this perpendicular distance will give you the anti-clockwise moment about this point. So you set them equal because it is in equilibrium. That's what they have done here. If you look at the calculation at the bottom here, you can see mg times d. Okay, so I think this is what they are assuming as this is the d. Okay, from here to here, that is the distance, simple d. So m is the mass of the broom. We have to use the weight. Okay, so mg, because it's the weight, the force times the distance. So mg is the weight, the force times the distance is the distance from here to here. Okay, from here to here, that is the distance d. Then here we have mg times x, capital M. You can see here capital M. Mg is this, the weight of this. Okay, the weight of this is equal to the tension here, because this is not moving. Okay, so the forces are balanced. So the weight force is acting on this. The weight is not acting on this, but we use it like this in the calculation because the weight here is equal to the tension here. Okay, so the tension force acting on the broom is equal to the weight force of this thing. So that is mg times the perpendicular distance is the distance from here to here, that is simple x. Okay. So mg times d equals mgx. Okay, then now if we know all these quantities, we can verify this equation. Okay, the left side of the equation should be equal to the right side because the object is balanced and the principle of moments apply. The principle of moments states that the total clockwise moment about any point is equal to the total anti-clockwise moment about the same point. So that's what they have here. Okay, so what happens is that g cancels out and we get x equals md. You can see md over capital M. Okay, now here the x was the distance from here to here. Okay, so if you want to So finding the center of gravity of an irregular rod. Okay. So if you want to find this distance, or let's say you can measure this distance, if you want to find the weight of the broom, then you can use this method. Any questions?
No, sir.
All right. Then there are some questions here. You can do this for homework and check your answers. I think I have sent you the solution, the answers to this book.
Yes, sir.
Okay. Then finally, the key definitions. Again, do you remember this is exactly what I told you that they can test you on, but also they can ask you the moments equation. Okay. So they can ask you what equilibrium is. They can ask you what is the principle of moments. They can ask you the definition of moment. Okay. So again, I am repeating the same thing again because it's very important. Okay. So you should know this. So that is actually not shown here, but you should know it. Okay. So if they have given the definition of moment, that is better because that also the test. Okay. So definition of moment, you should be able to state what equilibrium is. A body is in equilibrium if the resultant force and zero resultant moment. If there is zero resultant force and zero resultant moment, which is what I said here. Over here, for equilibrium, these two conditions have to be met. It will have zero acceleration because if the resultant force is zero, the acceleration is zero according to Newton's second law, F equals ma. Then the principle of moment states that a body will be in equilibrium if the sum of clockwise moments acting on it is equal to the sum of anti-clockwise moments. But what I told you is better. Okay. This book has much better definition. See, for center of gravity. We first will go through this. Okay, so yeah, then an object center of gravity is the point through which the weight of an object appears to act. Okay, so it's a very same definition, very similar definition here, where all the weight of the object may be considered to act. But about moments, you can see here this very good definition, and then this also is good about principle of moments. For an object that is in equilibrium, the sum of the clockwise moments about any point provided by the forces acting on the object equals the sum of the anti-clockwise moments about that same point, because it has to be about the same point. If you take clockwise moments about one point, and if it is in equilibrium, the sum of anti-clockwise moments about the same point only should be equal, because if you take two different points, then the moments will be different. Okay. If you take moments, say for example in this one, if you take moments about this point, the clockwise moments, and then you take anti-clockwise moments about, let's say, another point, let's say somewhere here, then the two are not equal. So the sum of clockwise moments should be equal to sum of anti-clockwise moments about the same point if an object is in equilibrium. Okay, so remember those four definitions: definition for moment, definition for equilibrium, then principle of moments, and center of gravity. Four things to remember. Okay, that is the end of moments. Any questions so far?
So that coupling movements.
What?
The coupling movements.
Oh, the torque of a couple. All right. Okay, I think there was some explanation here. We'll see. Okay, so here we have it in this other book, the Cambridge book. This is also very simple. Okay, now if you take a steering wheel, for example, now the steering wheel will rotate about this point, about the middle. Yes. You know, the car steering wheel, the middle of it won't move. Okay, but the steering wheel rotates about the middle. It can rotate about the middle, but this doesn't move about this point except rotating about this point. So we can take moments about the middle. Now what happens is when you apply a force like this, say you use one hand apply, then same amount of force you apply the other way. Okay, so that's why it's called a couple. Do you see? 15 Newton, 15 Newton. It's a couple of forces. Okay, so what we have here is, now the force is 15. According to the definition of moment, the moment is force into perpendicular distance from the pivot. The pivot or axis of rotation is here. to the line of action of the force. So it's a perpendicular distance from the pivot to the line of action of the force. So the pivot is here, or axis of rotation is here. The line of action of the force is here. The angle is 90 degrees. Can you see? Therefore, it's the perpendicular distance. So the total moment in this case is only all clockwise moments. Okay? So the total moment will be clockwise, and the individual moments are also clockwise moments. So this will cause the steering wheel to rotate clockwise. If you take the moment about this point due to this force, then this force will try to rotate the steering wheel this way clockwise. This is pushing up, so it will again try to rotate the steering wheel that way. So it will be a clockwise rotation. Okay, so a pair of forces like that in figure 4.25 is known as a couple. A couple has a turning effect. So here we have a turning effect. Earlier, when the principle of moments applied, there was no net turning effect. But couple, there is a resultant moment. So principle of moments doesn't apply, because if the principle of moments apply, then the resultant moment should be 0, meaning clockwise moments is equal to the anti-clockwise moment. But that is not the case here. Okay. But does not cause an object to accelerate. Okay, so another point here. A couple has a turning effect but does not cause an object to accelerate. Why? Because if it is to accelerate, there has to be a resultant force. If you look at this, you can see the total upward forces is equal to the total downward forces. Okay, the two conditions for equilibrium. The resultant moment has to be 0 and the resultant force has to be 0. But over here, in this example of the couple, the resultant moment is not 0, but the resultant force is 0. Do you see that? The resultant force is 0, because if you take the total forces in the upward direction, that is equal to total forces in the downward direction. Upward 15, downward 15, net is 0. So resultant force is 0. But since these two forces are not in the same line of action, there will be a resultant moment. It will cause the steering wheel to turn. So that's why they say, because the resultant force is 0, according to Newton's second law, F equals ma, if the resultant force is 0, then the resultant, if the resultant force is 0, according to F equals ma, the acceleration will be 0.
Yes.
Because it is the resultant force which produces the acceleration, not the other way around. Okay, the acceleration doesn't produce a resultant force. It is the resultant force which produces the acceleration. Okay, so since the resultant force is 0 here, there will not be any acceleration, because F equals ma. If F is 0, A is 0. So that's what they say here. A couple has a turning effect but does not cause an object to accelerate. A couple has a turning effect. So this 15 Newton 15 causes this to turn clockwise. So there is a resultant moment. So couple has a turning effect, but does not cause an object to accelerate. Does not cause an object to accelerate because the resultant force is 0. Okay, then we'll see. To form a couple, two forces must be. Okay, so here we can see. Now, very important. To form a couple, the two forces must be equal in magnitude. So equal in magnitude, because if it's not equal, then there will be a resultant force. But you know, there should not be a resultant force because no acceleration, but there is rotation. Yes. Okay, so equal in magnitude, you see here, upward force equals downward force. So net force is 0, no acceleration as a result. Parallel but opposite in direction. Parallel but opposite in direction means anti-parallel. Okay, so one is this way, the other is this way. They are parallel but opposite in direction. If you are taking mathematics, you will learn that this means anti-parallel. Okay, they are having the two lines, when you extend them, won't meet. If you extend these arrows, they won't meet, but because they are in opposite direction, we say anti-parallel. Okay, parallel but opposite in direction means anti-parallel. Then separated by a distance d. The distance is 0.2 plus 0.2. The distance between these two forces from here to here, that is the distance d. So the distance between the two forces is 0.4, separated by a distance d. Okay, the turning effect of a moment of a force is known as its torque. Okay, so torque of a couple. Now you learned what a couple is. So to form a couple, we need to meet these criteria. Then the turning effect or moment of a couple is known as its torque. Okay, so there we have a couple of forces. So the turning effect, we have a couple. So the turning effect or moment is called the turning effect. Another name for turning effect is moment. Okay, so the turning effect or moment of a couple is known as its torque. We can calculate the torque of the couple in figure 4.25. Now, you know, these forces have to be equal. If it is to be a couple, to form a couple, the two forces must be equal in magnitude, opposite in direction, but parallel and separated by a distance d. So to get the couple, we can take the total moment about this point, which is 15 into 0.2 plus 15 into 0.2. Okay, so do you see that 15 into 0.2 plus 15 into 0.2, which is 6, or else the easier way is 15 into 0.4. Can you see that? Both will give the same answer. So by definition, torque of a couple equals one of the forces into perpendicular distance between the forces.
Okay.
You can do it this way, the method that we used when we were calculating moments separately. So we take moments about this point. So this is the one clockwise moment, this is another clockwise moment, and then we add the two together, which is what they have done here. But if it's a couple, you know, the forces are equal in size. So because the forces are equal in size and they are separated by the distance d, which is 0.4, instead of taking it separately like this, we can directly, because the forces are equal in size, so because this is a couple, we can directly do it like this, 15 into the distance between them. So here we have 15 into the distance between them is 0.2 plus 0.2, which is 0.4. So we get this. Or if you look at this equation, you can see this is appearing twice, 2 times, 15 into 0.2, 50. So 2, you can say 15 into 0.2 into 2. Okay, 15 into 0.2 into 2, which is actually this. So the equation is this. This equation also you can study. Torque of a couple equals one of the forces into perpendicular distance between the forces. One of the forces into perpendicular distance between the forces. So let's take, for example, this force, one of the forces into perpendicular distance between the forces. So perpendicular distance is the distance which makes a 90-degree angle with the two forces. Okay, so from here to here, the angle is 90, here the angle is 90, so that is what, 0.4. So 15 into 0.4 will give you the torque for that example. Torque of a couple equals one of the forces into perpendicular distance between the forces. Then again, you can see what we learned before. For an object to be in equilibrium, two conditions must be met at the same time. The resultant force acting on the object is 0, the resultant moment is 0. So when we consider a couple, torque due to a couple, it's not in equilibrium. Because it's not in equilibrium because even though the resultant force is 0, the resultant moment is not 0. So here the resultant force is 0 because it doesn't cause acceleration. You can see clearly here they mentioned that, but does not cause an object to accelerate. So here 15 up, 15 down, the resultant force is 0. So therefore the acceleration is 0. So this resultant force is 0, but it's still not in equilibrium because the resultant moment is not 0. Okay. So for an object to be in equilibrium, both conditions have to be met. This condition, condition is not met in this example when it is a torque of a couple. Any questions?
Oh, sir, okay.
All right. So you understand then torque of a couple. Okay, I think that's the end of that that part. Okay, so we did couple, we did moment. You can do all the questions then. Okay, then shall we start the next one?
Okay.